Hello everyone, and today's lecture is we go over a Python example to solve minima cost flow problems using two different OR2. One we call the NetworkX. We used that in the previous lectures about minima spending tree. Another package we're going to introduce today is called OR2 tools provided by Google, and so both of them are open source software and package. We can illustrate that, and also there is a generic linear programming solver called PULP, and this one is we're going to use. Give you another video to introduce this, and also compare that with a commercial software called Gurobi to see what's going on. All right. So in this particular notebook, we're going to focus on using the tool for NetworkX and the OR tool, and we give you some of the information using Stack Overflows and all the GitHub to get some of these resources. As our lectures and mentioned so far, we define a minimum cost flow problems using giving a graph G with a set of node N and a set of edges called E. Xij represent the flow on the edges ij. Cij represents the so-called cost of a unit transportation cost for shipping A units on the edge ij. P sub I is the node supply or demand for a specific node I. Here is mostly we call it Uij. Uij is the flow capacity on the arc ij. Okay. The formulation is we already introduced in the class lectures, videos. We're trying to minimize the total cost on the network flow, but also we want to satisfy all the node and supply and demand, satisfying all the node demand and supply. And the first constraint, usually we refer as the flow conservation constraint, or referring as the so-called inflow equals to outflow. So for each node I on the network, okay, the outflow is all the flow. First term is all the outflow, which is ij, so it's flowing out from I for all the j's, minus the inflow, total inflow, which is for all the j coming into node I. So this usually means the flow out minus flow in equals to the node supply and demand. The last constraint is the upper bound constraint, or the flow capacity constraint and non-negativity constraint on the arc ij. The flow can. Here is a simple example we propose today, and this is a regular transshipment problem with two transshipment nodes, 4 and 5, don't have any node supply and demand, which is Bij equal to 0, and the green nodes on the left represent the supply nodes, and the yellow nodes on the right represent the demand node. They have a negative supply, which means and the number on the arc represents the cost for each unit of a flow sending down that arc. Okay, so here we're going to using a first we're going to introduce using NetworkX, an algorithm called minimum cost. So here is the example initially. Here we want to import the NetworkX. as the NX, for example. And then we're going to plot something. So we're going to using matplotlib. Okay. As the PLT. These are the standard library we're using for this example. So here we import this to. Next we define a digraph. Digraph is a directed graph, G, capital G. And after I defined it, we're going to adding some nodes into it. So G dot node. For example, I'm going to do the first node and give a demand equals to 300. Okay, and color. I'm going to color this equals to a hexaco. So this is the color I got it from PowerPoint, so hexaco, and I picked the color similar to the color in the picture. So see if this will work. Then I'm going to adding a couple more nodes. So here I'm going to do the same thing. I'm just going to cut and paste from my existing notebook. So give you speed up the process. I'm showing you I'm adding node 1s with a demand 300. Demand of negative 300, because originally we said that positive means the supply, negative means the demand. Here is since you ask for the demand, so I'm using negative as a supply in that case. So the rest of them I'm going to just cut and paste from my original program to show you for total of 8 different nodes. Each one of them might give us some different color, and the color code is mimicking the color codes over on my picture. Next we're going to add arcs to the network. Okay. So here we have, I'm going to using G edges. Okay. And the first edges is 1 to 4, for example. And I'm going to give a weight equals to 2, isn't it? 1 to 4, yeah. Edge equal to 2. So weight equals to 2, and capacity equals to 9999, for example. Okay, so this is since this particular example we don't have any capacity, so I'm going to put it into a larger number. Let's do another one. For example, 2 to 4. Okay, I'm going to do it within 1 to 5 in this case. Okay, I'm going to copy this. One to 5, and the weight is 1, I think. And the capacity is also, if you have any capacity, you can put it here. And the rest of them, I'm just going to copy and paste from my original program, so you get the idea what's going on. Okay. Just line it up a little bit. So here we see we finished defining the defining all the nodes and arc was a different color. Next things we do, we're trying to plot this network. Okay. Here what we do is we have a no position, which means I'm trying to mimic whatever position I have on this. Okay. So X and Y position, X and Y position. So roughly proportionally. So these are the coordinate X and Y. So no 1 is on the 1, 3. No 2 is on the 1, 2. No 3 is a 1, 1. So you see what is going on here. And so on and so forth. Next we're going to do is we're going to do the so-called adding the color into the node. So here we're going to do a no color, okay, equals to the color I have in the definition of the node. I'm going to extract that from the graph right here and make it a list. Okay, so here I'm going to make a list, convert whatever it is, make a list, and I'm going to get NX. I'm calling the NetworkX and get the node attribute. Get the node attributes. I'm going to call it from graph G and colors. Okay, but this is the color I wanted to have its value coming out. Okay, so I'm just wanting to have the yep, I have everything. Yep. All right. So this is I'm going to extract the color from the node, from the graph G, and make it a list. Next, we're going to probably can draw this already. I'm going to draw this network. Here I'm giving a little bit. I'm going to draw the G and also the node position. POS equals to the node position as I have. Okay, the list I'm defining. And I'm going to do with label, which means I want to label on each one of the node equals to true. And the font color for the label equals to red, for example. Let's do this first. Okay. Yep. Got a typo here. Okay. This is fairly rudimentary, and we have by default the first the no color equals to blue, and the red font size is not really showed up. So now I'm going to start adding the no color over here. The no color equals to the no colors right here. And okay, now as you see that as a little bit more look like the graph I have over here now. I can actually increase the size of no color, no size. Maybe 1,000. Now you can see that a little bit better than before. Slightly bigger. It's a simple graph. I'm just illustrate what is going on. And also I can change the node shape. Okay. if I want to. I just show you all the options, and you can have fun with it. Edge means hexagon. So yeah, just play with it yourself. This is an exercise. Next, we're going to adding the cost, our cost onto the drawing as well. So here I'm going to create a label 1. For example, I'm going to do that. Get edges attribute. From the graph G, and I'm going to get it from the weight. Okay, weight is basically the cost in this case. And I'm going to draw the network, draw the label on that. So what is that? Using the network, draw network edges label. Draw network edges label from, I'm going to using no position again. And this third one is labels equals to label 1 I just defined. And finally, I can do PLT show, actually force it to redraw the NetworkX. Okay, so now I have a very similar picture, looks like that over here. And you can exercise this yourself. It's just the process is fairly straightforward. So I'm spending more time on the presentation of the network and show you some basic trick how to adding edge color, no color, and so on and so forth. We did this in the previous notebook as well. The next iteration is we're going to solve the model using the network simplex method we talked about in the class. So here what we're trying to do is to see if we can, solving this is fairly simple actually. I'm going to have, it's just going to call nx dot network simplex. Solving the graph G, okay? And this is the only things we need to do for getting it solved. But we probably need something to storage the return the result, basically, from the solver. So here we'll have two things. One is the first is the flow cost, total cost itself, and the next thing is the flow dictionary, which is the solution. It's a dictionary. So here what we have is we're going to simply solve this using the network simplex method. Actually, in NetworkX, there are 3 different algorithms you can use to solve these minimum costs. And we talk about in the separate Jupyter Notebook lectures. But here today we just primarily focus on the network simplex method we introduce in our lectures and classes. So after that, I can print out the minimum cost, which is the total cost for the solution. And then we're going to print out each one of the dictionary items and each one of the solutions. See how that goes. So all I have to do is calling the NetworkX network simplex algorithm and on this graph G. All right. But however, I wanted to also be able to store the outcome, the output, the optimal solution returned from this algorithm. And the first one we'll have is the so-called flow cost, which is total objective function. Second is the flow dictionary, which is helping to print out the optimal solution. And after that, I'm just going to print out the optimal cost and then print out each pair of the flow, okay, and on the network. So here we can see that the minimum cost is 1500, and the flow between 1 to 4 is 100, flow between 1 to 5 is 200, so on and so forth. And you can actually very easily find out the optimal solution over here, okay? Directly visualize the art. So it's a very simple algorithm. And here I have everything into one cell, and you can copy and paste and make it in the Python program directly in the text base. So if you prefer to do that, that's fine with me. Okay, so I have it right here. The next part of our lecture is focusing on using the OR tools provided by Google, and it has an extensive built-in library for general optimization, linear programming, integer programming, network optimization, and many other algorithms. And these are the internal used by the Google developer and the Google engineers. But here we have plenty of example online. They have minimum cost flow problem, okay, and can solve knapsack problem, traveling salesman problem, vehicle routing problem. They have the existing notebook for you to download. Here I'm just going to provide a very simple symmetric example we have right here, or present in a parallel manner. Here, if you don't have the OR tools installed, you just execute this line called pip install OR tools, a progressive bar off, which you don't see it on your screen here. But I already have it installed, so we should be able to. And the introduction here is similar to before. I just want to walk you through the example. Actually, okay, execute this. Will tell me. Okay, so all the requirements are satisfied, and you can kind of know what is the required packages for this and the version. Okay, so the current version is 9.5 version. So firstly, I'm going to do NumPy. Okay, so defining the network right here, I'm going to using a little bit different ones. Here I have the instead of defining it in the pair like a dictionary we have right here, directly adding node. So here I'm going to using starting node in a parallel manner. First pair of node is 1 4 1 5 2 4 2 5 3 4 3 5 and so on and so forth. So this is defining the starting nodes and ending node. The next I'm going to do is the unit cost, which is the weight or the cost for per unit flow. I'm going to put it right here. They are all NumPy array, very simple to define that. Next we're going to do the capacity. So the capacity actually we have is NumPy array capacity. You can using NumPy to define much easier ones in 9999. You can using NumPy 1 times 9999. Okay, and here, but here, because of the parallel to the presentation, I'm using explicit form to define this NumPy array. Okay. Similarly, I'm going to define the node supply and demand. So here I'm going to do supplies equals to a NumPy array as well. Actually, I'm going to using a list. So 300, 300, 100, 0, 0, which is the transshipment node. Negative 200, that's the demand node. 200, negative 200. So this is corresponding to the node 1. Oh, sorry, the last one is 300. Okay. I can execute this as well. Move on. Sorry, maybe. Okay. I need to re-execute some of the definition. So lists range from 1 to 12. Total, I have 12 nodes. 12 edges, actually, 12 arcs. So now I'm going to import the OR tools I just installed. And from OR tools and graph to Python, I'm going to import the minimal cost flow algorithm portion. So I'm going to start building a models right here. My model is called minimal cost flow. I just defined it. Okay. Flow, but I'm going to using simple minimal portion cost flow. Okay, simple minimal cost flow. This is very simple, and after define the models, I can adding arcs into this model. So all arc equals to the model at arcs right here with the capacity and unit cost. See, this is the function to adding arcs. So starting node, ending node, capacities, and unit cost. Unit cost is right here. Okay. So using starting node, ending node, capacity, and unit cost. Next one, I'm going to adding node with the supply and demand. So I'm going to set node supply equals to the range of 1 to length of a supply plus 1. Why? Because the supply is from total we have 1, 2, 3, 4, 5, 6, 7, 8. 8 of them. But the starting node is 1. So there's the length of supply is 8, so it should be 1 to 9. Okay, 1 to 9, 1 to 8, I'm sorry. 1 to 9, so here we have 1, 2, 3. So the last number on here is not included. The length of supply is 8, and plus 1 is 9, so it's from 1 to 8 in that case. I'm going to give in the supply list over here, okay, over here, to define that. So define the model already in OR tools. It's very simple as well. So I'm going to solve the problem. Okay, I'm going to put a status as a return and solve the model. And OR2 is a little bit easier. All the solution is just a model.solve. So I'm going to check if the status equals to optimal. Okay, so we find the optimal solution, And the rest of them is very simple. I just, if the status equals to model optimal, I'm going to print, if it's not equal to optimal, there is an issue for that. A problem is infeasible or unbounded, so on and so forth. So here, this is just a warning sign. Have you able to come back to check what is wrong with your model? And here, if it's optimal, and I'm going to continue to print out the minimal cost and each pair of nodes and their corresponding capacity and the corresponding optimal flow solutions right here. So it is a very short and sweet portion, and the only thing is the way to define the models is using a whole bunch of NumPy array and the list for that. Okay, get a same solution, same optimal flow on each arc, and list the capacity and cost for your reference. And the bottom cell is just a alternative way to print out everything, the solution as well. So this is for your reference, and you are welcome to try it. And this part is mostly just showing you how to using an OR2. We're going to bring in more. The OR2 in the 9.5 and the 9.3 has a very significant upgrade and changes. I don't think the Google Teams has complete the upgrade yet. For example, some of the algorithms like shortest path are still not included in the transition. They already have it in the C++ interface, but Python interfaces. So far, some of the algorithm hasn't been transferred into the Python API at this moment. If there is a new update, and I will continue post video to keep you posted on this update. So this is pretty much a short lecture for this, and I would like to conclude this lectures and continue with the other algorithm we're going to introduce later on in the lectures, including cycle canceling, labeling algorithm, and successive shortest path problem, and the primal and due algorithm. To solve the same problems, I think NetworkX has all these various different algorithms. OR2 is the same thing. Several of them has option for you to choose. But here is the short version, the introductory version for how to set up a network, how to present a network, how to simply call the network simplex method to solve it, for using two different OR libraries. Okay, we'll see you in the next lecture.